let's now work through questions where we have the inverse function as an input. So you can see here we have sine of inverse sine x. So what we can do here is consider what we learnt in the previous module, whereby we can flip the output and the input. So if we flip them, then we also must change that sign to inverse sine. So this becomes inverse sine y equals to inverse sine x. And similarly to what I taught you before, because they're both inverse sine, I can also say that y equals to x. And now an important thing I want to tell you is that the only reason we can say that y equals to x for inverse sine is because there's a very narrow domain and range. So because it's a very narrow domain and range, therefore I can say y equals to x, where that's going to be very different when we have sine y equal to sine x. Okay, so remember, you can't do it if it's sine y and sine x. For this one, you will need to use the general formula or the general solution. Okay, just keep in mind this only applies when it's inverse sine. So this is the same for our inverse cosine as well. So we can just flip the input and output and make this into inverse cosine y equals inverse cosine x, and y equals to x. And again, because it's a very narrow domain and range, we know that it's only going to be between y equals to x, okay? And similarly with our inverse tangent, because it's a very narrow range in inverse tangent, although the domain is all real, because the range is very narrow, there's actually only one curve when we sketch that. So therefore, because there's only that one curve, we can say again that y will equal to x. So just remember, when we have your inverse, y equals to inverse something of x, this is when we can say y equals to x. Where if we had sine, cos or tan of y equals to the same thing x, we must use the general solution. Okay, so this is quite easy to remember because it's all the same for your inverse sine, cosine and tangent. But let's work through some questions because it is quite a new idea for all of us. So starting off here, we have y equals to sine of inverse sine x. Now let's consider the domain. So first of all, you're going to think, because we have sine of this, then this whole thing will be the input for sine, right? But remember, the domain for your sine curve is all real x, which means let's consider the domain for our inverse sine x. So if this was the input, what would the domain be? Yeah, that's right. It's going to be very narrow, isn't it? Between 1 and -1. And remember, with your equations, if you have a narrow domain and a wider domain, we always take the narrower domain to be true. Yeah, because that occurs within the wider domain. So that's going to be the true domain. So that's why for this domain, I'm going to be using this as the input. So I'll be using that to work out the domain. So I know that for inverse sine, when x is the input, it's going to be between 1 and -1. So my domain will be between 1 and -1. Yeah, that makes sense? Great. Okay, let's consider the range now. So the range, we're going to be considering this. So once again, because this is going to have the narrower range, that's why we consider that. So this is our output, and we know that's going to be between pi/2 and -pi/2. Now we want to make it look like that whole thing. So how can we do that? Well, we can apply sine to all of these values. So applying sine to all of these values, so this looks exactly like that. Can you see? I just need to work out what sine pi/2 is. So that is just sine of 90 degrees. So we know from our exact values, that's going to be 1. And negative pi/2 will be -1. So our range will also be between 1 and -1. And because it's equal to, we join those values. Yeah, so there's no asymptotes there. Now, let's finally consider the graph. So this is what we learnt in our first page here. So this is a box we want to draw within. This is our equation. Now we change the input and output, and we change the sign to inverse sine. And because they're both inverse sine, we can say that y equals to x. So we're actually only drawing y equals to x, which is just a straight line from here to there. And because it's a very narrow domain and range, we're only drawing from that point to that point. Can you see that? So this is going to be our graph for sine of inverse sine x. Okay? I think it's a lot of work for this, but I think once you've done this once, you'll always stay with you because it's not really something you expect to come out from this equation. But you can see why this is our final graph. Okay, so this is when we had inverse sine as the input. Now let's have a look when we have inverse cosine as our input. So here we have cos of inverse cos x. So with the domain, it's going to be a very similar concept with our previous question. So when we consider this as the input for cos, the domain is going to be very wide, as in all real x. So we want to consider the narrower domain, and that's when we use this x as the input. So when we consider x as the input for inverse cosine, the domain is going to be exactly between 1 and -1. So because that's a narrower domain, we hold that to be the true domain. So this is our domain here, 1 and -1. So let's graph that and our curve here. Now let's consider the range. So the range, what we want to do, very similar to the previous question, is because we know the basic range for that, right? We know that inverse cos x must be between pi and 0. We use that to start off with, and then we want to make it look like this. And how we're going to do that is to apply cos to each of these values. So you can see that this now looks exactly like the equation up here. And now we just need to work out cos 0 and cos pi. So cos 0 just equals to 1, and cos of pi equals to -1. So our range is going to be between 1 and -1. So we're going to be wanting to sketch our graph between these values. So considering the graph, it's going to be within this box, yeah, that we can just imagine in our mind. And now let's think about what it's going to look like. So we have this here, and we're going to make this input into the output and the y as the input. Now the cos is going to become inverse cos. So that's why inverse cos y equals to inverse cos x. And because they're both inverse cos with very narrow domain and ranges, we can say therefore y equals to x. So we just draw that in. And remember, never with arrows, because it must stop where the domain and ranges stop. So you can see here, this is actually ends up being exactly the same graph as we sketched for inverse sine. Can you see that? And it also follows the same processes. So it's good because I think you can compare the two and see why this ends up being the same. Okay, now we want to look at inverse tangent as the input. So here y equals to tan of inverse tan x. So the domain for this is going to be interesting because for when we have tan, the domain is going to be, what was it? Everything except for a few values. But we want to consider this x. And we know that when this x is applied as an input for inverse tan, your domain will be all real x, which means it'll be all those values here. And for the range, similarly, because we know that the range for this is between pi on 2 and -pi on 2, we start off with that. And now we apply tangent to all of those things. So we want to find out the tangent of -pi on 2 and pi on 2. Now, what do we remember about a tangent graph? That's correct. With these, it's going to be infinity. So what we have is between -infinity and infinity, which essentially just means all real y. So it's going to be between all of real y here. So these actually keep going when we sketch them. So when we sketch the graph, we don't actually have a box because these keep going forever, don't they? And considering this, so same idea, switch the input and output, becomes inverse tan y, inverse tan x, y equals to x. So we sketch y equals to x, but the main point of difference is that this y equals to x will keep going. Can you see that? Because the domain and range are both all real x and all real y. So you have to draw that arrow there. That is the main difference between the previous two graphs. And if you don't draw the arrow there, you miss the point of this entire question where we find out all real x as a domain and all real y as a range.